Equality case is found, essentially speaking, using two different tools. So the first tool is something called as a rearrangement, where you take any function and you kind of radially rearrange it, and you can show that under radial rearrangement the Sobolev inequality improves. And then the other is to, once you show that your minimum is obtained by a spherical function or a radially symmetric function, you may then use the calculus of variations to, for example, find out what that function is. Now, it turns out that this much works for the Sobolev inequality. For the Gagliardo-Nirenberg inequality, equality cases in full generality are still not known. So only some baby cases and some very special cases are known for the Gagliardo-Nirenberg inequality. There are two known methods to obtain equality cases for the Gagliardo-Nirenberg. One is the previous method that I said. So that's basically rearrangement plus calculus of variations. The other method, and that can be found in a monograph by Figali, which is called as I think it's called as stability in functional and geometric inequalities. In functional and geometric equalities. Survey, right? Or is it a monograph? Sorry, it's a survey. That's right. In stability in functional and geometric inequalities. In this particular paper, you can find how a higher dimensional Sobolev inequality, which is tight, can be used to prove a tight GN inequality for a particular choice of indices. So this happens because the equality function in the particular Sobolev inequality considered at the starting has a nice structure which kind of decomposes into two parts, and because of that you can explicitly create the equality case of the GN inequality that you need to prove. So for example, this can be done for some of the lower cases, n equal to 2, p equal to 3. I think p equal to 2, n equal to 3, for example, it's known. And that's what's presented in Figali's paper. So these are the remarks that I wanted to make. And now I can come to symmetrization. But the equality cases of GN are not known in general. Those of Sobolev are known thanks to the paper of Talenti. So what is symmetrization fundamentally? Symmetrization should be thought of as an operation that preserves area, or at least when Steiner came up with it, he came up with the idea that it should preserve area but reduce the perimeter, because he wanted to prove the isoperimetric inequality using it. However, while we'll be highlighting why it preserves area, we won't be highlighting why it reduces perimeter explicitly in this lecture. We'll just be proving the Brunn-Minkowski using it, and automatically the isoperimetric inequality will drop out of that. So what we need is eventually proved. Now, let me define symmetrization. In order to define symmetrization, I need a kind of a hyperplane or a vector which will act as the kind of object around which I will symmetrize. So let me make the definition of a symmetrization. So you start with a bounded set. And you start with any n-1 dimensional. Okay, I'm working with D. So D-1 dimensional hyperplane. Well, it should not be a hyperplane. It should literally be a subspace. So it should pass through the origin. Then the symmetrization, let's call it B, of A around V is defined as follows. What you do is, let me draw a diagram. Let's say for convenience that A is something like this and V is this hyperplane that you see here. So we're working in one dimension. sorry, in 2 dimension. V is a hyperplane. Sorry, I'm not defined it yet. I'll explain to you how it works, right? So what's going to happen is that we're kind of going to create an object that is symmetric around V. So I have labeled here for you A and V, and I'm going to create an object that's symmetric around V. How? What we do is we consider these lines which are passing orthogonal to V. So there are many lines that are orthogonal to V passing through various points. Some of the pink lines that I have drawn here, they are lines, so they will of course extend all the way to infinity. You take these lines and you look at the, how they intersect with A. So for example, a particular line like this intersects with A between this segment and this segment. And similarly, if you take a line like this one, it intersects between this segment and this segment. And those segments, you adjust them so that they are symmetric around V. So these segments that you see here, these will be kind of moved and made symmetric to V. So moved.
And these may not be just segments, right? There may be unions of segments also.
Yeah, sure.
You look
And
at the
they may
total
not,
measure and
they
then
may not even be, I mean, they may not even be unions of segments. They could be something terribly irregular because I've just assumed that A is bounded.
right.
What I have drawn in my representation is something, a very regular object. But as it turns out, there is no need for this particular intersection to have any structure. But you kind of make it into an interval and then move it symmetric to V. So let me quickly explain.
Sorry, so
So
you're going to assume something on the A itself, namely that all these cross sections are at least Lebesgue measurable or something.
yeah, sure, sure,
Okay.
sure.
Just a mild hypothesis, right? Okay.
Yeah, that's required once you start taking the area of those objects. A priori, you do not need any such assumption.
But even for the symmetrization operation, you will need it, right?
Oh
To say
yes,
that I'll take half the measure on the left and half, yeah, yeah.
that's right. That's right. That's right. You will
Right.
need it. You will need it. So I should add that. So perhaps I will do that. So A is a measurable bounded set. I should add that. Right. So if A is a measurable bounded set and V is any d-dimensional one subspace, then how do you create the symmetrization? You take any line which is perpendicular to V, and you define the intersection of B with this line. So B intersection L will be a closed interval with midpoint in V, or empty. It could be empty as well. And the second and more important criteria is that the volume, that is to say the one-dimensional volume of B intersection L, will be equal to the one-dimensional volume of A intersection. So it will be adjusted. It will be adjusted so that the one-dimensional volume at each stage is exactly the same. And finally, of course, the third one, if A intersection L is empty, then B intersection L will also be empty. So it's a kind of line by line symmetric adjustment of A around a particular hyperplane.
Why should B intersection L be an interval?
B intersection L does not need, no, B intersection L is by definition a closed interval. We make it a closed interval.
That is the defining property for B. Not
Yeah,
A is
that's
the
right. No,
original
A
solid. B is the
intersection
new
L
one.
could have any structure. It needs to be measurable. That's right. A intersection L definitely needs to be measurable. If I'm not wrong, A measurable will imply A intersection L measurable for all lines L.
No, that's not true. This looks like more than symmetrization. Suppose A is a single point,
Yes.
then what would this be? It will be a full line, is it?
No, it would
Extending
not
both.
create a full line. So for example, let's say A is a point. This is
Yeah,
A. And let's say this is V. I'm trying to draw it, sorry. This
yeah.
is V. Then all that will happen is that point A will become another point, which will be lying on that perpendicular from A to V. So it will come here. So this will be the symmetrization of A around B. If I'm not wrong, if a set is measurable bounded, then its intersection with every line will also be measurable and bounded. Otherwise, I'll have to put that into the hypothesis as well. Thankfully, I'll be working with regular enough sets, but if I'm not wrong, that should be true.
No, that is not true. That statement is not true, but you will be using nicer sets, I guess.
Yeah, that's right. That's right. Okay, so then what I will do is that I will add it into the hypothesis instead. So let's not assume that A in RD is bounded. Let's assume that it's measurable, and in addition that A intersection L is measurable. So let me just do that. Yeah. So A is a excuse me. It's a measurable set, and such that A intersection L is measurable for all lines L. So typically this will be the case, for example, for convex sets and so on. There should not be a problem for convex sets and so on. Right. Yeah, this needs to be part of the hypothesis. This is typically not, but I think, yeah, thank you for pointing this out, because I think we will be working with sets which are good enough, if I'm not wrong. Right. So there is another notation that I'll be using. Yeah, sorry. No, it's not. No, it's not. Okay, if somebody can give like a concrete counterexample of this phenomena where A is measurable, but A intersection L is not measurable for a particular line L, that would be nice.
Take a non-measurable set in the line. Because
right.
it has zero measure, it is measurable in the higher dimensional.
Right. Okay, so just to make the example more explicit, you take a non-measurable set and put it in R2 instead of R. In R, and you put it in R2. Right. Right. So yeah, thank you for pointing.
Just one question.
Sure.
Suppose I take A to be singleton, what prevents me from taking B to be empty set?
What? No. The condition that if A intersectional is empty, then B intersectional is empty. Oh, I see. Though that's an if and only if. Excuse me. That's
okay.
Right. Excuse me. Yeah, that I forgot that. Right. So you define B intersectional as empty if A intersectional L is empty. So I didn't write it as an if and only if, but yeah, I mean that's how it should be. Yeah, right. So we insist.
So this
right.
Sorry, this symmetrization, you're choosing a direction, right?
Yeah. So once.
So the thing is that you also want to, I mean, it could be that you are measurable. I mean, the condition you want is true for some direction.
We'll start with sets for which it's true for all directions, so that we can apply.
Okay,
there is a point at which we will need to make sure that symmetrizations are available in every direction.
Okay, fine.
We simply need to do that. And
okay,
while I haven't checked it because of this sudden interruption, if I'm not wrong, for compact sets and convex sets and so on, sets with some amount of regularity, these measurability criteria should go through.
Okay, thanks.
These should go through, for example, for compact and open sets, for example. Maybe I think in general for Borel sets also perhaps, but not fully sure at the moment. Yeah, sure. Yeah, so if A intersection L has different components, it still is Lebesgue measurable, right? That's all that matters. It has a particular area.
I see.
It's V is a set, right? Capital V is a set. You're just making sure that B intersection L is an interval that lies on the same line but it's adjusted so that its midpoint lies exactly on V. Okay, so let's say A intersection L has, that doesn't matter. So for example, okay, so the doubt is as follows. What if, for example, the intersection of A with V looks like this? Okay, excuse me. Yeah, so let's say the intersection looks like this. You're talking about a situation like this, is that right? Then what will happen is, so if this is A, then let's say this is V. You find the total length of those intervals. Let's say they're both intervals of length half. Then the total length of those intervals is 1. So what you do is you just create an interval of length 1 around that point. Sorry? Yes, B intersection is an interval. By definition, it's an interval. So then they'd have Lebesgue measure 0, right? Same as 1 point. Then you'll just put 1 point around the center. So for example, let's say these two are intervals of length half, then their total length is 1. So you just put a single interval of length half and make sure that its intersection point is the same as the point P that I have drawn here.
I have a question. Sorry. Yeah.
Yeah.
Yeah. The same thing that Professor B.V. Rao asked. Suppose I have a countable set as A intersection L. Then do I just put 1 point as the B?
Right. Then you put 1 point as B.
So maybe that should be added. That not just the empty set part, but if it's a measure 0 thing, then it's a single point that you put for B. Maybe that should be an extra axiom.
Is that
Not implied by these
that
three.
follow from the rest?
No.
I mean,
Yeah, that follows from here.
Closed interval. You're right. You're right.
that
Closed
follows
interval.
from the fact that it's a closed interval.
Aha,
Because
you're right.
cannot. Yeah, right. I mean,
Yeah.
you get.
Okay. Thanks.
Yeah, right.
I think basically what you are doing is you are looking at the projection of A onto the subspace, and then at each point of the projection you are building a line with the same measure. That's it.
Yeah, that's right. That's right. So at each line, you're just checking the intersection. Hopefully that intersection by hypothesis is measurable. Take its measure, find a closed interval of that exact measure, and make sure that it is positioned on that same line and symmetric to V, so that its midpoint lies on V. And you can do this for every single line, and that's how you get the symmetrization. So as Puri ma'am was saying, every hyperplane that every n-1 dimensional subspace is also equivalent to specifying a particular vector and taking everything orthogonal to it. So saying that we have a
is not unique, right? I mean, you can translate V.
Sorry, what can you translate?
You can have a translate of V that will also work as a symmetrization, right?
No,
Parallel to V.
it's you have to make sure that V is symmetric around V. So the question is,
No,
does a
parallel
translate
to
of
V,
V work?
parallel to V if you move it around.
No, you see. Oh, right. Okay, I get what you mean. Right. If you move the hyperplane V around, then yes, the V will also get moved around. So yeah, there is an element of translation invariance to what we're doing here in some sense. Well, I mean, it's not.
Huh?
It is. I mean, no, I don't think it works. I
No,
don't think it works.
No, there is no translation
You have to
invariance.
sort
As
of
I
pull it in
said,
the same direction.
You look at the projection of A onto your subspace,
Yes.
and around each point of the projection, you build a line. Okay, that's it.
Yeah, that's right. That's right. You can think of
Appropriate.
it that way. Yeah, that's right. That's a good way to think of it. So you can also think of it as kind of projecting A onto this hyperplane, and then at each point of that projection, creating a line segment protruding outside of a particular length. Right. So yeah, we were talking about n-1 dimensional subspaces here, but every n-1 dimensional subspace also corresponds to a particular vector u, in the sense that everything that's perpendicular to u creates V. So in that, if we symmetrize say a set T about U perf, then we call the symmetrization as TU. Then TU denotes the symmetrization. But we will have to switch between notations. So that's the reason why I just need to occasionally drop this notation as well. I need to sometimes use the hyperplane and I need to sometimes use the orthogonal vector. So I'll draw it out. Let me just draw it out visually once again. So here is like a large scale example. This example is prepared keeping sort of everything that's coming forward in mind. So this example will be in 2D. So we're in D equal to 2. I'll draw a two-dimensional object and I'll symmetrize it about a particular hyperplane. So first I'll draw the hyperplane. So this is the hyperplane V. You can think of it as also, the orthogonal complement of the x-axis. So that would be 0, 1, 0. Orthogonal complement. And I'll just draw the body. Just give me a second. The body will look as follows. This is copied from Krantz, this particular image, because there are some features of it that will be significant as we go ahead in this lecture. And let's create a hole here, for example. So everything in here is T. Let's call this object as T. And so T is good enough that it will satisfy the hypothesis. And what will be the symmetrization? On the other side, let's look at V here. Let's look at TU now. So we're looking at TU on this side. What will happen is that you just need to look at the slices, right? So let me draw the slices in pink, perhaps. So you'll just monitor these slices. These are the lines which are all kind of perpendicular to T, which are perpendicular to V, excuse me. And you kind of look at what is the volume of T intersection each line and start adjusting the intervals. So if you look at the top, initially there's like an increasing amount of volume that's getting covered. So if I make like a rough drawing of that, it would look something like this, something like that, not drawn to scale. Then what happens is, if you notice, there's like a small patch where it's constant, where like the width is constant. So there's be a little constant patch. And then there's suddenly a hole. So the hole kind of reduces the volume suddenly. And then again, there's an expansion outward on the left-hand side. So there's like a little expansion out on the left-hand side. You can see it's kind of symmetrically developing with respect to V. And once the hole actually stops, once the hole ends, then that particular line segment also becomes part of T, which should have been in the hole. So that again sharply sort of increases the width of T. And then there's a little. So the starting from here to here, I have drawn lines in blue on the left-hand side. The intersection of T with that particular line is nearly constant. So you kind of get a constant here. And then it shrinks to 0. So it kind of looks like this. So this is how the symmetrization TU will look. It gets rid of the hole, but around holes it may behave a little discontinuously, as we just saw. But the most important thing is that it kind of peters out towards the end as well. So it retains symmetry, and as you have seen from the construction, it is also symmetric with respect to B. Right. Now the question is, why do we introduce symmetrization? As I said earlier, symmetrization preserves the area. So one can check. I'll just leave this as a check because this is this is Fubini's theorem. You just need to make sure that you're fixing the hyperplane and then integrating along the lines and then adding up the lines. So it's just a Fubini theorem check that if a set, say T, satisfies the hypothesis to allow symmetrization. And if V is any hyperplane, then the symmetrization is also a measurable set. And I think it will continue to satisfy the symmetrization hypothesis. This is something that I have not verified. This is important because we will need to symmetrize objects that have been created by symmetrization. We need to create sequences of symmetries. Therefore, this is important hypothesis for symmetrization, and it has the same volume. Let's call the symmetrization as T prime, and the Lebesgue measure of T prime is equal to the Lebesgue measure of T. So symmetrization literally preserves the volume, but there's a lot more that it preserves. For example, one can show, at least I'll sketch it out next, that if you have a compact subset, then its symmetrization Tu will also be compact for all u in S d minus 1. For all unit vectors, basically. If you symmetrize about the hyperplane created by any unit vector, compactness is retained. So here's a proof of that. To show that something is compact, you need to show that it's closed and bounded. Boundedness is something that is fairly straightforward. You can check that. That's because if T is bounded, then T intersection any particular line segment is also bounded. And then you're just compressing that particular line segment, compressing the contents of that line segment into a closed interval. So boundedness is fairly clear. It's closure that could be a tension point. However, to check closure, what you need to do is the following, right? So let's say you have a, I don't know, you have like P1, P2, you have a sequence in T, and let's say it is converging because T is compact, the Pi will definitely converge to some P which belongs to T. What you need to do is the following. What you do is you know that P1 that belongs to a certain line L1 which is perpendicular to U perp. So there is a unique line which passes through P1 but which is perpendicular to the hyperplane that we are considering. And similarly, P2 is also contained in a particular line, and so on. So you get this sequence of lines L1, L2, and so on. The idea here is that because PIs are converging to P, the lines Li will also converge to the line L as convergence of sets. And you can also check that the lines intersected with T will then converge with the L intersected with T as well. And when this happens, you can apply a Fatou's lemma. To be more precise, in this case, you apply the reverse Fatou's lemma. So by the reverse Fatou lemma, no, the convergence in sets is literally in a pointwise sense. Literally in a pointwise sense. So the convergence here is in the pointwise sense. The reason is because the reverse Fatou lemma only requires the the indicator functions of each to converge pointwise. That's basically the theorem that we're applying here, right? So you can check by the reverse Fatou lemma.
By the way, since you're looking at PI in Li, each has a not just is there a unique line perpendicular to U perp, there's a unique point in U perp on which sits below PI, right?
That's right.
And the point is that point belongs to T intersect U. Oh, okay. Sorry, my mistake. Yeah.
All right. already.
All I was
Yes.
going to say is, okay, in the symmetrization, that point will belong to TU intersect U perp, which is but okay, then you don't know it's compact. Okay, sorry.
Yeah, that's right. You don't get
Ah.
compactness from there. That's a good point, right? But anyway, by the reverse Fatou lemma, what you can show is that the sets. This convergence that I have written here, this is just a convergence of indicator functions of those particular sets, right? This is just fairly straightforward, right? So by the reverse Fatou lemma, you can show the following. You can show that I'm just hiding a few lines of work here. Nevertheless, the sort of one-dimensional Lebesgue measure of these intersections will be less than equal to the Lebesgue measure of L intersection T. And once this happens, what you need to do is you need to go back to the definition of symmetrization, right? Prior to going back to the definition of symmetrization, realize that if Pi converges to P, then the distance from Pi to the hyperplane U perp, just by continuity of the distance, is also equal to the distance from P to U perp. So the distance from P to U perp is important because that tells you whether or not P will belong in the symmetrization, right? Because the distance from P to U perp is if P belongs in U perp if and only if that distance is small enough so that that particular volume of the line intersecting T, which contains P, has enough Lebesgue measure, right? So what can we get from these calculations? Well, we start with D of P U perp, and we just wrote above that it's the limit of this dpi U perp. But what do we know about the PIs? And what do we know about dpi U perp? Now, dpi U perp is less than equal to this particular quantity. Why is that? That's because if you look at what symmetrization does, symmetrization makes sure that it kind of, you've got, this is the line segment, right? The length of the line segment is Li intersection T, that particular intersection. Now, once you've kind of created a line segment out of that, then every point that will lie on that is in the symmetrization that will lie on that line segment will be at distance at most half that particular measure. And then because of the reverse Fatou lemma, that's just half the size of L intersection. I'll be writing subscript 1 here to indicate that I'll be taking the one-dimensional Lebesgue measure of that particular line wherever necessary. And this condition here is sufficient for P to lie in the symmetrization. And therefore, closeness is obtained and compactness is obtained similarly. Right. Now, one can check similarly. Now, this is, the fact that compactness is preserved is a great thing. But one can check, for example, it's written in Kranz's book that if T is open, then TU is actually, it's not open. You can check that it's not open because we're deliberately taking closed intervals, but it's definitely a G delta set. So a G delta set is a countable union of open sets. Sorry, countable intersection of open sets. You can check that it's definitely a G delta set, and it's not true that if T is Borel, then the symmetrization of TU needs to be Borel. This is not true, and a counterexample also can be found in Kranz's book. So it's not like T preserves even weak structures such as Borelness and openness, but it preserves compactness, and as I will mention next, it also preserves convexity. Borel sets are sets which are generated by open sets. You take all countable intersections, all countable unions. Right. So if T satisfies, okay, if T is convex. I'm sure if T is convex, then its intersection with every line segment will also be a line, with every line, its intersection will also be a line segment. Therefore, it will automatically, I think, satisfy the hypothesis. So if T is convex and U is any vector about which we wish to symmetrize, then TU is also convex. So here is again a sketch of that proof. Convexity is essentially a property of three lines, if you think about it, right? Let's draw a diagram again. So let's say this is T. I have drawn here something T. This is convex. It's not necessary. So in my diagrams are not, of course, representative of all situations. It's possible that the symmetrizing the vector about which we want to symmetrize, it's possible that it need not intersect T at all. But in my diagrams, I just make sure that it intersects T. So for example, let's take this as UPerp. It's not necessary that UPerp intersection T needs to be empty, but that doesn't make a difference. The logic will not change much. So now, as usual, let's take 3 points X, Y, and Z, and let's understand why convexity is preserved. So let's take 3 points X, Y, and lambda X plus lambda Y, which I call as Z. So here is a line segment between them, and here is the point Z, which lies in between them, right? Now, if we need to understand whether Z lies in the symmetrization or not, what we need to understand is in the symmetrization, only these lines matter. Only the perpendicular lines matter, right? So we look at the perpendicular line through Y. We look at the perpendicular line through Z. We look at the perpendicular line through X, and it's everything is about the volumes of these. Everything that you see here is about the volumes of these intersections. These intersections, that is basically speaking, if I call Lx, Ly, and Lz as the unique lines which are perpendicular to UPerp passing through XYZ, then the intersections of these lines with T is what matters. Their Lebesgue measure is what matters, right? And as you'll see, there is a containment relation between them, and then we will apply the one-dimensional Brunn-Minkowski inequality, which I will assume that has been proved using elementary methods to conclude. So how does that work? Well, let's be formal at this point. So Z, let's call Z as some lambda X plus 1 minus lambda Y. What you will observe, so this is an observation, is that because T is convex, sorry, no, they're in T. X, Y are points in T, and even Z is a point in T. So far, nothing. So we have not made any remarks about the symmetrization as of yet. So it is not clear, for example, what points X and Y will go to in the symmetrization. That's not clear at all. But I don't plan to make that clear either. Because you see, that's not even required. All we need to know is those measures. That's all we need to know. So the observation to make here is that if you look at this particular set, let's say lambda times T intersection Lx plus 1 minus lambda T intersection Ly, what this particular sum that I have written here, it will actually be contained in T intersection Lz. That's because anything in lambda in Lx plus 1 minus lambda Ly, it will be contained in Lz. Because Z is lambda X plus 1 minus lambda Y, and T is convex. So this observation that I make here is key. And once I make this observation, I will assume that each of T intersection Lx, T intersection Ly, and T intersection Lz are one-dimensional sets and I'll apply the one-dimensional Brunn-Minkowski inequality, which can be proved using. So the one-dimensional Brunn-Minkowski inequality can be proved using the fact that you can, if you have open sets, you can make them into countable unions of intervals, and therefore it's enough to study finite unions of intervals. So it becomes much easier that way to just directly approach open sets and then compact sets. So by the one-dimensional Brunn-Minkowski inequality, you will get that lambda times the one-dimensional volume of T intersection Lx plus 1 minus lambda times the one-dimensional volume of T intersection Ly is less than equal to the one-dimensional volume of T intersection Lz. Right. And you can put a half at each point. And this is enough. You see, this is enough because why is this enough to prove symmetrization? Let's go back to that, to UPerp or whatever. If I draw these line segments now, what will happen in the symmetrization? In the symmetrization, if I look at the line Lx, and what will happen, how will the symmetrization's intersection with Lx look like? It will be a particular line segment of some length, right? It will be a line segment where the it will be symmetric, and its length will be T intersection Lx. And similarly, the length of at the point y, it will be some T intersection Ly, the volume of that. Now, because of this relationship that I have written here, the line T intersection Lz is so large that is, or at least it has big enough Lebesgue measure that if I draw any line between these 2 points, like for example, this black line that I have drawn here, or this black line that I have drawn here, the line through Lz is big enough that it will intersect all of them because of the relationship that I have written above. So you see this point that is here, that point is, lambda of the point in Lx intersection lambda of 1 minus plus 1 minus lambda times the point in Ly, the point that I have highlighted in big pink. That will be part of the symmetrization because the length of T intersection Lz is large enough to accommodate it. And because of that, we're actually done. You can show now that the symmetrization is convex because those particular points, they will end up belonging in the symmetrization because the length of T intersection Lz is big enough.
If you look at the slides, just pretend it's the flat. So this distance isn't a convex function simply because the 1/2 is convex. So this distance to the edge is a convex function, right?
Right.
And same goes for
right.
And the width is actually average of 2 convex. So wouldn't it be like it's essentially saying the fact that if I have 2 convex function and take the mean, it's again a convex function.
That's right. That's right.
So we don't even need any Brunn-Minkowski. We're just using the fact that a function is convex. It's not going to be specific of this one.
Okay, I need to understand that more. Yeah, I'm still not fully sure of to register that.
This convex shape take a slice like this.
Yes.
Now at each point I can associate the height function, right?
Right.
As a function.
Yes, that's convex. That's convex. It's like concave. Yeah, it's right. That's right. The distance is subadditive, so it's right.
This is also like concave this way.
Yes.
And whenever I'm making the distance like average of these two, I'm essentially making sure that this height is average of these distances.
Right.
So in effect, I have 2 concave functions, let's say, and I'm trying to say that the average is also concave.
That's right. Yeah, the average of concave functions will retain concavity, right?
Yeah. I think, I hope.
Okay, so an alternate concavity based argument based on the distance to UPerp function has been proposed. I'm still not fully sure about its veracity, but I'll definitely make sure to work on that and see if I can get something out of it. But for now, this should be a good enough proof. So.
Another point I had in the beginning, we're talking about measurability.
Right.
So although we cannot conclude measurability at every line, but when we define product measures, then we do have that almost everywhere here this line is visible.
That's right. That's right. But not every line, right?
Yeah,
That's
not
the
every
issue.
line, but almost.
Correct.
So you'll have.
Yeah.
So I guess for your inequalities probably it doesn't matter. Like because you take
No, I think every symmetrization matters because we can't we have trouble with sets of measure zero. We may have trouble with sets of measure zero. Yeah. Yeah. No, it is better to assume in the hypothesis that every it is measurable. Its intersection with L is one-dimensional measurable. Let's just assume that. Yeah. Let's just make it easy. So before I move on to my next result, what I'm going to do is I'm just going to state a very standard fact. And this fact has to do with the Hausdorff metric. So
one more question.
yeah,
If
sure.
you have, so you start with compact, you end up with compact. You start with convex, you end up with convex.
Right.
If you start with a, let's say, two-dimensional or whatever, if you start with a polygon, do you end up
Right.
with a polygon? It is both compact and convex. Yeah.
I mean, see, the problem is that there's I expect that. Yes, I would expect that. But the thing
Right.
is, a lot of objects can cut down to a polygon. For example, if you notice the example I drew above, the example that I drew above, this is a polygon. What I have literally drawn here, right? I mean, T that I drew, it's a polygon with a hole in it. So that ended up restricting to a polygon. And I think it has to do with the fact that if you take that, kind of that intersection of L function, it's good enough for you to for it to not have too many breaks, and you can introduce vertices at the points where it breaks perhaps. So yeah, I expect that to be retained. This the diagram that I drew is a representative example of polygonal relation being preserved, except for the hole, of course.
Right.
Right. Yeah.
Uh,
Right.
Yeah,
Yeah.
but okay,
Another
even still,
another remark.
even still, probably you should not have. I guess okay, if you don't allow for holes, etc. Okay, fine. Yeah. Okay, thanks.
No, another thing to observe, yeah, like Yogesh said, another thing to observe is that if you kind of slide the perpendicular line to V down or whatever in the direction of V, then the if you're looking at a polygon, the volume of that intersection is growing linearly in some sense. So that seems to be another concept. That might be a reason why you might expect straight lines to appear in the symmetrization, in the boundary of the symmetrization. You may expect straight lines to appear for that reason. So yeah, I would expect that. That's a really good remark. I'll think about that. I'll think about that as well. So yeah, just coming to a really standard fact. If you take all non-empty compact subsets of RD and you take the Hausdorff metric on these. So the reason why we take the Hausdorff metric is that we want this particular property that I'm going to mention next, which is basically the Bolzano-Weierstrass property. So this is a metric space with the Bolzano property. So the set of all. So the set of all non-empty compact subsets of RD with the Hausdorff metric has the Bolzano-Weierstrass property. What does that exactly mean? So to spell it out mathematically, if you have compact sets C1, C2, and so on, such that there is a capital M greater than 0, such that Ci is contained in the ball of radius 0m for all I, then Ci has a convergent subsequence. In the in the Hausdorff metric. So this property is important. It's important because the proof of Brunn-Minkowski will involve us. I mean, just by approximation, we will involve ourselves with good enough, regular enough sets. And with those regular enough sets, we will need these topological results in order to allow for symmetrization to help us out. Right. Now, here is a nice lemma that talks about how symmetrization will affect kind of holes in a particular structure, right? So let me explain quickly how this works. So you take, let's say, T1, T2, and so on as compact subsets of RD with the following property, that each one is a successive symmetrization of the previous with respect to a particular hyperplane. So such that you have a sequence V1, V2, and so on of hyperplanes. Or I should not call them hyperplanes, excuse me. I should really call them as n-1 dimensional subspaces to avoid confusion. D-1. Such that Ti plus 1 is Ti symmetrized with respect to Vi. Ti symmetrized with respect to Vi. So the point is, if Ti has certain lacunae, the same will be retained in Ti plus 1 and in fact further added to. That is what is going to happen. So now we will introduce three quantities. If R, T, and epsilon are such that Ti for a particular I is contained in the ball of radius 0r closed, and you have a point P around which the lacunae will be created, which is in the ball of radius 0r's boundary, such that this intersection is empty. So I'll draw a diagram, of course, explain what I mean. So this particular intersection is empty. So what is this intersection? Let's draw T. So suppose, I don't know, this is, first I'll draw the ball of radius 0r. So let's say this is the ball of radius 0r closed. And let's say this is T. So it looks something like this, right? What I'm doing is I have found a point P and a point epsilon such that the boundary is not kind of hitting T until distance epsilon at least. So let's say this point is P and you've drawn a ball of radius epsilon such that so this ball is the ball of radius epsilon. So this distance here is epsilon. So ball of radius epsilon around P intersected with the boundary. So you look only at the boundary and that isn't hitting Ti. And that isn't hitting Ti. So that condition has to be assumed. If this is assumed, then what will happen is for all j greater than equal to I, or rather for all j greater than I, excuse me, not only will the same continue to hold, Tj is equal to phi. Furthermore, what will happen is that the hole that you see here, the lacunae, will kind of be reflected across the symmetric hyperplane as well. It will be so for example, let me draw a symmetrizing hyperplane here, say V. Then what will happen is if you reflect the point P across V, okay, sorry, this is not the reflection. This is the reflection. You'll get a particular point here, which is some P prime. And what will happen is the lacunae at P will transfer to the lacunae at P prime. So B of P prime E intersection the ball of radius 0r intersection Tj is phi, where P prime is P reflected on V. So reflected at V. Yeah. So I'll give a visual proof of this.
Just one
Oh,
question.
around VI, excuse me. Right.
Yeah, just a question.
Yeah, sure.
Why do you have a sequence? Your theorem is only about Ti and Ti plus 1, that's all, right?
Yeah, this sequence is required in anticipation of the fact that we need a sequence later. So actually, I could have stated this just for Ti and Ti plus 1.
Okay, fine. Thanks.
Right. So this could have been stated for T1, V1, T2 also. But the problem is we require a sequence later on. And what we're trying to say with this result is that, of course, so as you see, it's enough to prove for j equal to I plus 1. Because there is, what will happen is you can then repeat the argument with I plus 1, I plus 2, and so on. So it's enough to prove this for I plus 1, which means I did not have taken a sequence in the first place. But for convenience, I've taken it as a sequence because I'll be applying the theorem for a sequence, or at least for a finite sequence. So proof, yeah. Yeah, that's right. That's right. That's right. Yeah, so the way to think of this is that if Ti is not intersecting the ball of radius 0r, then Ti plus 1 will also not intersect the ball of radius 0r. Furthermore, there will also be another region of non-intersection created by the reflection of the other intersection. We're running out of time. Sure. Okay. Right. No, because this session, it looks like it will, probably I can't finish. Okay, let me try. Right. So, I mean, the proof is pretty much visual. I just, I think, I mean, it's fairly clear that, yeah, sure. Okay. So, right. So what you do is the following. It first of all, it suffices to show for j equal to I plus 1. Suffices for j equal to I plus 1 for this to be shown. Now, what do you do? Remember, it's again all about the perpendicular lines. It's all about the perpendicular lines, right? So you take the line that's passing through P. Let L be the line passing through P. Now, if you take any other line, L prime, such that its distance from L. So what does the distance between two lines mean? It literally means the geometric distance between the two lines. For example, if you have a line here and you have a line here, then you draw, then they're let's say they are, in this case, they are both perpendicular to the particular hyperplane in question, VI. So in this case, it's just literally the geometric distance between them. So if this is L prime and this is L double prime, then this particular quantity here is the distance. So if that particular distance is less than epsilon, then you can check that the Lebesgue measure of T is definitely less than 2R. You can check this. That's because, again, if you look back at the diagram, okay, I'll just draw it again for convenience. So if this is the ball of radius 0r, this is the set T, and let's say this is the point P that I have drawn here. The line, if let's say the symmetrizing hyperplane is this one, P, the line L, which is passing through P, is this one. Let's say this is L, right, which is perpendicular to V. So sorry, L perpendicular to V. And we take any line that's just on epsilon on either side. So we could take this one. This could be L prime, or even this could be L prime, right? Any of these lines could be L prime, and because of the assumption that it doesn't intersect Ti, because of the assumption that those boundary points don't lie in Ti, these gaps will be reflected in the symmetrization. So what will happen in the symmetrization is that because the length of that particular line segment or that particular intersection is less than 2r, even the length of that particular intersection will be less than 2r. So what will happen is that you have, let's say, V here, and you will get line segments, but of length which are less than 2r. And once they are of length less than 2r, it must happen that those line segments must not be hitting the boundary. And what's happening is that because you're kind of symmetrizing of around lines passing through P and which are perpendicular to V, if anything is happening at P, it will also happen at P prime. It will also happen at the particular line, at the particular point reflected across, because you're choosing the interval to be symmetric around capital V. So if L prime intersection T is less than 2R, the symmetrization Ti plus 1 does not intersect, Ti plus 1 intersection that particular line. Excuse me, that's an aberration. Intersection that particular line, intersection B0R will be an empty set. And this will happen across the reflection as well. And this completes the proof. So what we've shown is that these gaps, they kind of get reflected across. And because they get reflected across, there is a way to use this mechanism that we've invented here and combine sort of various symmetrizations to show the next big theorem. So the relevance of the theorem that I'm about to show now, which I hope isn't the last, is that this is the key step that Jakob Steiner missed in his proof of the isoperimetric inequality. What he was able to show is that if there is a minimizer, then it's the ball. He was not able to show, for example, that the ball is a limit of a particular sequence of minimizers. What we're about to show here is that a particular set of regular enough objects closed under symmetrization and closed under the Hausdorff of distance must contain a closed ball. So that is the theorem. So it's an existence statement, and that is basically what Steiner missed in his analysis of the isoperimetric inequality. So if you take any non-empty family C of non-empty compact sets, in RD, which is closed under the Hausdorff metric, and under symmetrization by any hyperplane, by any n-1 dimensional subspace, by any n-1 dimensional subspace, then it must contain a ball. Then there exists a ball P. So what we will be doing is that we will now then, as we proceed ahead, we will be working with a particular family of that kind and using the existence of a ball to show the Brunn-Minkowski inequality. Because as we know, balls are equality cases of the Brunn-Minkowski inequality. Balls are part of equality. Oh, yeah, and excuse me, this ball will be centered at the origin as well. Furthermore, this ball could also have radius 0, and it could have radius 0. So that could happen, for example, I mean, a ball of radius 0, closed ball is just a single point. So it's possible that might be a single point, but it's definitely true that a ball of some radius is there, centered at the origin. And the proof is the following. It's a proof by contradiction. So how does it work? It works as follows. So you create the quantity R, which is the infimum of So you consider all sets which definitely lie inside a ball of radius 0r. So the infimum of all S such that there is some element of C which lies in the ball of radius 0, ball of radius S around 0, right? And you have these guys. Now, if R equal to 0, then you're done. Because if R is equal to 0, then the set of minimizers will actually shrink to a point in the Hausdorff distance, in the Hausdorff metric. So that particular point is then the ball that you need. However, so what we will do is we'll assume R greater than 0. And once R is greater than 0 and you consider a minimizing sequence, any such minimizing sequence will also then be inside a ball of significantly large radius, because any convergent sequence is a bounded sequence. So, or it is a bounded sequence. So by the Bolzano-Weierstrass property, you can actually get a convergent sequence. And because this particular, because the maximal radius of containment is a continuous function with respect to the Hausdorff metric, you can get a set that's completely contained in the ball of radius 0r, but also belongs in C by continuity of maximal, by continuity of this function. I can make it explicit. Continuity of max T in C, norm T with respect to C. So this particular function is continuous in the Hausdorff metric. So using this, you can get this particular minimizing object. And what we will claim now is that T is in fact the ball of radius 0. T is actually equal to the ball of radius 0. So how do we prove this claim? As I said earlier, the proof is by contradiction. So so T is a compact set. T is a compact set. So if it's not equal to the ball of radius 0r, but it's contained in the ball of radius 0r, then B0r minus T is open. So it will contain at least a ball. So B0r minus T is open. Hence, or rather it's the closure, excuse me. So you can find a point, say P, and a radius epsilon, such that the ball of radius epsilon around P is contained in this B0r set minus T. Again, let's draw a diagram. So let's assume that T is B0r exactly minus a ball. For the sake of convenience, let's say that, this is the ball of radius 0r and T is exactly ball of radius 0r minus a set for convenience. So let's say this is, the ball of radius epsilon around P or something like that. This particular ball that I have drawn here, let's say that it's the only part of B0R closure which is not part of T. So everything else is in T. Let's draw a symmetrizing plane. Say V. So this is V. What you do is you remember the diagram that we drew earlier. Holes were absorbed. Now what happens to these holes when we symmetrize about a V like this? What happens to these holes is that they will actually move to the boundary. First, they'll move to the boundary, you see. Let's draw the line that passes through P, which is perpendicular to V. And again, if you look at any line which is at most epsilon away from it, that will also carry information from the hole from it. So let's say this is L prime and this is L prime and so on. What will happen is in the symmetrization, because the volumes of the intersections of these lines with T is smaller than 2r, when you symmetrize, gaps will appear at the boundary. So post symmetrization, now let's say this is the ball of radius 0r. What will happen is that when P gets pushed to the boundary, or P won't get pushed, but when you take the intersection of that particular line L with the boundary, you will get lacunae at those points. So P will kind of look like this. So T symmetrized about V. About P. So that will look like this. Let's say call it T prime. So it will have these holes. You will get these holes in these positions. Hole here, and you'll get a hole here. And now once you have holes at the boundary, you can move them around by the previous lemmas. And you only need finitely many movements because of compactness of the boundary. So once you have BP epsilon such that BP epsilon is contained in this particular intersection, then you can symmetrize with respect to any P and see that you will get at least one point, say P1 and epsilon 1, such that P1 is in the boundary and the ball of radius P epsilon, sorry, I'm calling it P1 epsilon 1, intersection with the T intersection with the boundary is empty. So you have one point, and now you start moving around that point. How do you move around that point? By abstractly using the compactness to pick other points to which you can move this lacunae. And how do you do that? You do that as follows. You, by compactness, of the boundary, you pick points P2, P3 up to Pk such that the boundary is contained in the balls of radius Pi epsilon 1. In this case, we have a particular epsilon 1 from I equal to 2 to k. So now these points are the points where these lacunae are going to get moved. We are going to move them to these points, right? So let's again make sure that we have the diagram in place. So this is a diagram, and this is P1, say. This is P1. Let's say, for example, another point P2 came up here. And maybe this is P3, and so on. How do we move the lacunae from P1 to P2? If you recall the previous lemma, if you symmetrize about a particular hyperplane, a particular n-dimensional subspace, then the lacunae gets reflected about that particular n-dimensional dimensional subspace, right? So what you do is you pick an n-1 dimensional subspace, say V1, such that the unit vector, or whatever, the vector P1 minus P2 is orthogonal to V. So that is to say, you join the line P1 and P2 in this case and take the perpendicular n-1 dimensional subspace to it, and that will be V1. Now if you symmetrize about V1, the previous lemma tells you that if you symmetrize a okay, so let's call the result after the first symmetrization as T1. So let's say T1 is T symmetrized by some initial choice V. So the earlier V was arbitrary. This V1 has been chosen keeping P1 and P2 in mind. So then symmetrize with respect to V perp to get, or I shouldn't call it V perp, I was calling it V1, excuse me. V1 to get some object T2, say. But then T2, by the previous lemma, we will have that T2 intersection the ball of radius pi epsilon intersection the boundary is empty, but now for I equal to 1 and 2. So now this will be true for P1, but post symmetrization it will be true for P equal to 2 as well. And now you can just keep going. So this will be true. So what will happen is now you will get, now what will happen is, let's say this is the ball of radius 0r. T2 will now miss P1 and it will miss P2. So it will kind of look like this, P1 and P2. So this is T2, but then you can create a T3 and so on. So proceeding like this, we will reach Tk plus 1. So having gone through, T1, T2 on all those points, we will reach Tk plus 1 such that Tk plus 1 intersection the ball of radius pi epsilon intersection the boundaries is empty, but for all I equal to 1, 2 up to k. However, because of the union containment relation that we wrote earlier, this is the same as saying that Tk plus 1 intersection the boundary of this ball is empty. And unfortunately, the way we have chosen our set, it's closed under symmetrization. And Tk plus 1 belongs in C. And therefore, Tk plus 1 is contained in a ball of radius 0s where s is less than r. And that's a contradiction. Because by definition, we have chosen r to be the minimal such point. So this is a non-constructive, but definitely an illustrative proof of the fact that a ball must be part of the conversation when we talk about symmetrization. Do we have time? It's 3:30.
How much more you need?
No, there's far more to do. At least 20 minutes worth of material.
Sarvesh, you can also take up some time next time if you don't. I have no problem.
Yeah, I mean, I can go through like a slower lecture next time, maybe perhaps. This time we have definitely exceeded because of questions and issues.
Sure, that's fine with me. I mean, we don't have to. Yeah, we can discuss this actually, Sarvesh. We can see how to do this.
Sure. But yeah, it's good. I think this lemma is like a good finishing point because this lemma is sort of, it's very key to understanding why like this argument of Steiner, for example, was very restrictive and it could not extend to Brunn-Minkowski. So the fact that we can exist we can assert the existence of a ball as a minimizer is a big step. So it's nice that symmetrization can achieve this much. Maybe next time we can show that symmetrization will actually finish off the Brunn-Minkowski inequality in full.
Yeah, I think it's fine. So let's just discuss this. Maybe we can see. Sorry, I think
Sure.
there is some.
Can
Sure,
I just
yeah,
ask a question?
Yeah, please go ahead.
Yeah, please go back to the statement of the theorem.
Yeah, sure. Just a second.
Yeah, you see, what I was just wondering is the following. Suppose you take R2 and you
Right.
take the 4 points minus 1, 1, 1, 1, okay, 1 minus 1 and minus 1 minus 1, okay, 4 corners of the square, okay.
Right.
Now, suppose you look at the symmetrization of this on all hyperplanes, okay, one dimensional.
Yes.
Then
Yes.
I think you will get certain sets which are either 2 points or 4 points, okay. I think
Yes.
if you
Could
look
you get more
the
than a 2
collection,
points?
yeah, you might get even 2 points also, right?
Yes, 2 points definitely you can get.
Correct. Okay, but you won't get 1 point. That is my feeling. If your I want to apply my theorem to this collection of sets, all possible symmetrizations of the four corners. Okay.
Are the four corners treated as separate sets, or is that just one set that you're continuously applying symmetrization?
Oh, I start with one set consisting of the four corners.
Okay,
only
right,
one set.
Right.
And
Yes.
then I look at all its symmetrizations. Okay.
Right.
Then this, I think, satisfies your condition.
This does satisfy. I think you should get a ball of radius 0, right?
No, unless you get a singleton, how do you get ball of radius 0? I think any symmetry.
Okay, I think this is how you can do this. So
you do get a
if
singleton, right?
you have a square consisting of 4 points, you first start with this hyperplane that you see here. You first start with this hyperplane, and then that gives you a 2-point set, like so.
Okay,
and
okay.
Then you take the midpoint of those two.
I see. Okay, okay.
Those will combine. Right.
Okay, okay. Thanks.
Sure. Yeah. I expect this to work. I mean, we've shown something stronger. We've actually shown that the sort of the infimum like is attained in. I mean, we can center such a ball around the. We can even center it at the origin. So on. So we've shown something a little stronger than just the existence of such a ball. So, right.
Yeah.
I'll be more precise next time. Maybe I missed this measurability condition because I was reading from a classical textbook and I think it missed that assumption. But I'll make sure to read from a more thorough source next time. Yeah.
But you anyway stuck to compact sets. Then everything is compact, right? There is no problem.
Compactness and convexity are okay. So compactness is good and convexity is even better because of the fact that every intersection is a line segment.
Yeah, but convexity is too much to assume, but you can prove isoperimetric inequality for compact sets is good. I mean, reasonably general.
Sure. Yeah. Right.
I just had a very small remark. This theorem, I mean, just the details are there, but one can say that this R is a continuous function, I guess, on the space of sets in Hausdorff metric. And you're showing that this is a compact set, it attains a minimum. And your other observation shows the minimum can't be anything other than a ball.
Correct. So this is also a kind of this is a mini isoperimetric inequality in some sense. This is a not isoperimetric, this is an I mean, whatever this function is inequality.
Yes.
Minimum radius function.
Yes.
Yeah, that's a good remark. Thank you. So in my next lecture, then I'll make sure to finish off symmetrization. I'll mention I'll probably come up or at least list proof of the fact that compact sets and convex sets satisfy the hypothesis of being symmetrizable. I'll at least mention that, go through a sketch of that because now that is a necessity. And then I will continue my argument all the way through to the proof of Brunn-Minkowski inequality as I stated in my very first lecture.
Sounds good. Yeah.
Yeah. So I'll need another lecture, right?
So we'll maybe post these details once we discuss this. We'll post these details on Teams, and maybe since there was some confusion about the link, I'll keep the same link for the meetings going forward, so that there is no confusion regarding that. Yeah, maybe we can all thank. Unless there are more questions, are there more questions?
None, yeah.
Okay, so maybe we can thank Sarvesh once.
Yeah, thank you. This one just got
All right, so I'll just stop recording. We can continue the discussion.
Yeah, sure.